All right, guys, looks like we're recording. So this is the review for Exam 5 material on trigonometric functions and modeling here. Get my pen to work. So trigonometric functions and formulas, I'm sorry. So let's get started. We're going to start with the last problem, actually, first. Let's go back down to the very last problem. This is kind of our trig workout again. And so remember, you will be given these formulas eventually, but the first thing you'll be tested on whether you know them or not. And then once you do that, you'll turn that sheet in, and then you'll be given the formulas. So on here, what do we want to do? Basically, you just want to fill in the blanks. So for the trigonometric model, what we want to do is be able to say what the amplitude is. And the amplitude comes from this times A. So remember, from transformation point of view, that times A is on the outside. So it's actually a vertical stretch. And that gives us an amplitude of almost A. You have to put in an absolute value. So absolute value of A. Because if A is negative, remember what it does, it actually reflects it over the x-axis. So we don't really want the negative involved. So we take the absolute value just to say how high it's going to stretch that wave, basically. And then the period, well, the period is given by this b right here. And so remember, the period of sine is 2 pi. So you take 2 pi, and then b's on the inside. So it's actually kind of like a horizontal shrink. And so you divide it by b. So 2 pi over b. And then finally, this phase shift is actually given by c and b. So remember, you can rewrite this as a times the sine of, and we can factor that b out. So b times x minus c divided by b in parentheses plus d. And this c over b is the horizontal shift. We think about it in terms of transformations. So the phase shift, which is the horizontal shift, is c divided by b. And so there are the formulas for the amplitude, the period, the phase shift, given that trigonometric model. All right, then for the law of sines and the law of cosines. So remember, we're working with this generic triangle right here. And to write these down, the law of sines, I kind of give you a blank. So you can kind of use this if you want as a quotient. So you can take the sine of A divided by little a, and that's equal to the sine of B divided by little b, and that's equal to the sine of C, or angle C, divided by little c. And that's what we call the law of sines. In the law of cosines, it's kind of like the a generalization of the Pythagorean theorem. So it looks like this: c squared equals a squared plus b squared. And of course, it's not exactly equal to just a squared plus b squared, because it's not really a right triangle. It's any old triangle. So there's a slight correction term here. So 2 times ab cosine of angle C. And now we move on to the sum and difference formulas. And these are a little bit tricky for me to remember how to do. So I have a silly little saying to kind of help me. So when I do the sine, I know the sine has the same sign. So if it's plus, the same sign means it's plus. The sine has the same sign, so that means it's minus. But remember, something's always different. So the sine has the same sign, but something's always different. So it goes sine, cosine. That's the difference. So it's sine of alpha, cosine of beta, sine of beta, cosine of alpha. And there's the formula for sine of alpha plus beta. And then over here, you do the same thing. The sine has the same sign, but something's different. So that's the sine cosine. So sine alpha, cosine beta, cosine alpha. And then, of course, a cosine, it has a different sign, but yet something's always the same. So here you have a plus, so it's a different sign, so it should be a minus. And the same is cosine, cosine. So it goes cosine alpha, cosine beta, and then sine alpha, sine beta. That's the sameness. And then for cosine of alpha minus beta, it has a different sign, so it's a plus. But something's always the same, so it's the cosine, cosine. So cosine alpha, cosine beta, sine alpha, sine beta. And that's how I memorize these sum and difference formulas, right? The sine has the same sign, but something's always different. The cosine has different signs, but something's always the same. And then double angle formulas, these aren't too bad. Sine of 2 theta, I just memorized straight up. It's not that hard. So it's just 2 sine of theta, cosine of theta. And the tricky one really is this cosine of 2 theta. So when I think of cosine of 2 theta, I'm like, oh, it's like the Pythagorean identity. So remember the Pythagorean identity is cosine squared theta plus sine squared theta is equal to 1. And that's the most famous in all of trigonometry, basically. And so it's just like that one, but instead of a plus, you put a minus. So that's how I remember it. So it's cosine squared theta minus sine squared theta. And then there's 2 other versions of this formula for cosine of 2 theta. And each of them come from this Pythagorean identity over here. So if you solve this for sine squared theta and plug that in right here, when you solve for it, this will be 1 minus cosine squared theta. So you'll see you actually get 2 cosine squared theta and then a minus 1. Whereas instead of solving for sine squared, if you solve for cosine squared theta and then plug that in over here, you'll get 1 minus 2 sine squared theta. And that's the other formula for cosine of 2 theta. So this one's tricky because it's got 3 different versions. Of course, the most important one is this one. And that's the one I use most often. But the other 2 pop up from time to time. And so when you see them, you want to recognize that's really a cosine of 2 theta. And so those are the double angle formulas. And then we move down here to the power reducing formulas. And so what these do is they reduce powers on cosine and sine. So if you have cosine squared theta or sine squared theta, you can reduce it to kind of a linear thing. And so I actually have these memorized because they're so easy in a sense because they're the same. So the cosine squared theta is 1 plus cosine of 2 theta divided by 2. And sine squared theta is the same thing, 1 minus cosine of 2 theta, except you have a minus in the middle, of course, divided by 2. And so there's a lot of symmetry here you can use to remember these because they're basically the same thing. One's just a plus and the other's just a minus. And notice, if you solve this for cosine of 2 theta, you get this. Versus if you solve this for cosine of 2 theta, you get that. So if you know this here, the power reducing formulas, you get those 2 other versions for free. So there are a couple of ways you can remember them. Okay, so there are our formulas from this section that we have to be familiar with and memorize if possible. And now let's go back to the problems. And so let's start back up here at number 1. And let's knock these out. So on number 1, this is just a graphing problem. And you do have a graphing calculator to kind of help you along here. So maybe we'll use our graphing calculator to check our work here. But let's take a look at this problem here. And so what do we have? We have this trigonometric function, and we can identify our pieces here. So there's our A, here's our B, here's our C, and here's our D. So we have y equal to 3 times sine of 2x minus pi over 3 minus 1. And we're going to use that to answer the problems below. So the first thing we're going to do is find the amplitude. So remember, the amplitude is the absolute value of A, which equals the absolute value of the number 3. And of course, that's equal to 3. And then we're going to find the period. And so the period, remember, is 2 pi over b. And so that's equal to, well, our b is 2. And so 2 pi divided by 2 is just equal to pi. And then finally, our phase shift, where our phase shift is c divided by b. And so that's equal to, well, here's our c, which is pi over 3. And then we're going to divide that by our b, which is 2. And so remember, 2 is like 2 over 1, so I'll multiply it by the reciprocal. So pi over 3 times 1/2 is equal to pi over 6. So there's our phase shift, pi over 6. Now what we want to do is use these numbers, the amplitude, the period, and the phase shift, along, I guess, we do have one more up here, right? We have d, which is a vertical shift down 1 unit. So we'll have to use that too eventually, vertical shift down. 1 unit. But we're going to use these to graph one period of the function. So if you look at part D, it says graph one period of the function on the graph above. Make sure to label the maximums and the minimums. So let's do that. So to do this, what we're going to do is we're going to start with this graph of the sine function. So remember the sine function, you just have to remember the first part, right? The starting point. When you plug in 0, you get out 0. When you plug in pi over 2, you get out height 1. So put that up there. When you plug in pi, you get back 0. Pi over 2, 3 pi over 2, you get negative 1 and back to 2 pi. And so we're just going to kind of sketch this, which is kind of hard on here, but best I can. Oh, get my sleeve up here. So we just want to sketch this. It goes down and it waves back up. So there's a graph of sine of x. Right? So my first thing I want to graph is just y equals sine of x. Up here, maybe I'll keep track of what I'm doing. All right. Now, it doesn't really matter the order I apply these physical quantities to, like the amplitude, the period, or the phase shift. So I'm going to just do one step at a time. So I'm going to start with the amplitude. So the amplitude of 3, all that does is it stretches it vertically by a factor of 3. So, you know, this point can't be stretched vertically, but this point right here can go up to 3. This point right here can't be stretched vertically because it has height 0, but this point can. At negative 1, it's going to go to negative 3. So you're going to multiply basically the outputs by negative 3. And then this one's going to stay right there. And so then we can plot those points. And there we go. That's y equals 3 times sine of x. And now we can take in this period adjustment. So the period is pi. And so what that does is it basically just shrinks or compresses that graph. Or I didn't say shrink. It shrinks it basically horizontally, right, into pi, right? So you want to basically go from here to here in one period. So notice what's going to happen is basically this point over here is going to go right there. And so everything else has to be compressed in side of it. So this point right here is going to go right there. This point right here is going to go right to the middle right here. And this point right here is going to have to go right to the middle right here. And so everything's going to be compressed between 0 and pi. And then finally, and maybe we should start labeling some points over here, because then we're going to shift this over pi over 6. So if we want to label some points here, we should probably label this point because it's going to get kind of tricky here. So what is this point? Well, the output's easy. It just has height 3. And the input is halfway between 0 and pi over 2. So that's pi over 4. So this is pi over 4. And this one down here is halfway between pi over 2 and pi. So that would be 3 pi over 4. It's like 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4 is pi. And so 3 pi over 4. And then comma, and that's negative 3. Right, so there's the max and min. And so now what that one looks like is y equals 3, and that's sine of 2x. And now we have to include the phase shift, right? So the phase shift is move it to the right pi over 6. Now that's pretty tricky to do, but the way that I drew this sort of coordinate system is that these little spots right here are pi over 6s. So notice this is 1/3 of pi over 2, which is pi over 6. So what we're going to do is just move each of these points, these green points, over into the middle, basically, or at one slot, basically, right? So this green point is going to go right here. This green point right here is going to go right there into the middle of that slot. This green point is going to go right here. And then this green point is going to go into the middle of that slot. And then this green point is going to go right here. And so now I can just connect these dots here. I think this is a pretty tricky little problem to do. Okay. But that's what it looks like. And again, we should label these. Oh, so maybe I write right here. So y equals now, this looks like 3 sine of 2x minus pi over 3. So we're actually not quite done yet. But let's label these points so you can see what we did. So that new blue point right there, you know, it still has height 3, but the input is right in the middle between this slash and that slash. Or if you like, just take pi over 4 and add pi over 6 to it. So maybe right here, let's do it right here, I guess. So right here, I can take pi over 4, because that was the input right here, and you're just adding pi over 6. And so notice that's not an easy common denominator, but 12 goes into 4 and 6 go into 12. So really you just multiply top and bottom by 3 here and multiply top and bottom by 2 there. And we get 3 pi plus 2 pi, which is 5 pi over 12. And so this point right here is 5 pi over 12. And this point down here, well, again, the output is still negative 3, but what's the input? So you take 3 pi over 4, and you're going to add, what? Pi over 6 to it. And so again, you got to get a common denominator. So we multiply top and bottom by 3 here and by 2 here. And so we get 9 pi plus 2 pi, which is 11 pi over 12. And so this one is, I'll do it in blue so everything stays the same here. So 11 pi over 12. All right, we have one more movement to make. So don't forget, we do have that vertical shift down 1 unit. So we take each of these blue points and just move it down 1 unit. So that blue point goes down 1 unit. 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 And again, we just connect the dots. And it looks like this. And of course, we're supposed to label the maximums and minimums here. So if you label these maximums and minimums, you know, what happens here? The input stayed the same. So it's still 5 pi over 12, comma, and a 3 went down 1, so it went down to 2. And down here, the input is still 11 pi over 12, but the output changed from negative 3, moved down, so negative 4. We're just changing the outputs on those. And for fun, if you want, you could actually probably label these things here, right? These points here if you want to, but it doesn't ask us to do that. But if you wanted to, notice you could label this as being pi over 6, comma, negative 1. And you could go through all of these and do those, each of those points, because we did count pi over 6s, right? So it's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. So this would be the point 4 pi divided by 6, comma, negative 1. And this would be the point, well, you have 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6. So 7 pi over 6, comma, negative 1. And in fact, 4 pi over 6 actually reduces. So if you want to, you could write that as 2 pi over 3. Right? So it's really 2 pi over 3 if you reduce it. But there you go. That's how you solve that problem. And that's a really tricky problem. But there are ways to kind of make it less tricky. I chose kind of like the hardest possible problem version I could give it to you. So I probably went to the hardest. Notice if the phase shift was like pi over 4 or pi over 2 or even pi, it makes the problem a lot easier to do. So that's kind of like the toughest version. Now, you can check your work on these. So let's check our work. Let me bust out my calculator here. Forgot to pull it up. So let me get it out. And so just to check my work, what I want to do is just put it on my calculator to see if it looks somewhat the same, right? So if I can make it look somewhat the same, then that would be good, right? So if I can move this around, geez, come on, man. Get that. So on my screen here, guys, let me see if I can't hide this and then pull it around. There we go. So now I can pull it a little bit. All right, so there we go. So on my calculator, what I'm going to do is I'm just going to plug this in. Make sure you're in radian mode. So I'm in radian mode and hit y equals. And then we're just going to graph this. So we'll type 3 sine of 2x and then minus a pi and then divide it by 3 and then in parentheses and take away 1. And then for the graph, I'm going to go to my window and I'm going to go from 0 to 2 pi. I'm going to make it look just like the graph that I have here, basically, right? So if you look at this, it goes from 0 to 2 pi. And then I'm going to make my window and then my y min to be -4 and my y max to be +4. And then hit graph and see if I don't get something that looks similar, right? So you kind of see here, oh yeah, it's going up, and up, and up, and up, and up. And then I stopped it right here, of course. You can make this look exactly alike if you change the scale. So for fun, we haven't done this yet, but you can change the scale to count in terms of pi over 6s. So you see that x scale there, you can make that a pi divided by 6 and then hit graph again. And it'll count in terms of pi over 6s. So each of those little slashes are slashes on ours. So you can kind of see where it's sort of passing through that little. If you draw a line right here at -1, you see how it matches up with what we have, So it looks pretty good. So I'm going to check it off, to check my work there. And on the exam, what I like to do is I just like to check off the problem. So I'll put a check right there. If you see that question circled on my exam, that means I need to go back and look at it because I didn't have a way to check it, or I'm still kind of not sure if it was right or wrong. All right, let's move on to the next problem. And so this one's a little bit similar to the last problem in the sense that we're going to graph this function, but we're going to do this mostly with transformation. So let's take a look here. So we want to use a graph of y equals sine inverse of x. So that's what they give us here, the graph of y equals sine inverse of x, and some transformations to graph this function, sine inverse of x minus 2 minus pi over 3. And then state the domain and range, and this should say using interval notation. All right, so first, let's just identify our transformations. So for our transformations, hopefully you see there's 2 of them, and we're going to write them down. So what are the 2 transformations being used here? Well, the first transformation is that -2. And so what is that? If you take away 2 on the inside, it's a horizontal thing. So it's a horizontal shift. And I always think, if you say -2, I want to say to the left 2, but it's on the inside. So it's actually to the right. So horizontal shift to the right 2 units. So that's what that -2 does on the inside. And then that minus pi over 3 is on the outside. And so that's actually a vertical shift down 3 units. And so let's do this. And I might do this one in blue, guys, because the graph's given to me in red. So minus pi over 3. So let's do this. We'll just kind of do one at a time. I'll just use the graph that they gave me here, but I think I'll label the points, right? So this is the point 1, comma, pi over 2. And this is the point 0, comma 0. And this is the point -1, comma negative pi over 2. And the first transformation is this horizontal shift to the right 2 units. So I'm just going to move this point to the right 2 units. So I just go over 1, 2. So 1, 2. So this is the point 2, comma pi over 2. And this point, I go over 2. So 1, 2. And so this is the point 2, comma 0. And this one goes over 2. I guess I did not draw this to scale very well, did I? Because if I go over 1, 2, I wind up right here. That's not too bad, I guess. So, 1, 2, and so that's the point, what? +1, comma, negative pi over 2. So it's like -1 goes to 0, goes to 1. And now I just connect the dots the best I can, trying to reflect the graph I was given before. So it looks something like that. Now I'm going to apply this last transformation, which is a vertical shift down by, not 3 units, right? Pi over 3 units. I think the red distracted me, right? So maybe you saw that, but make sure you make that change. You know, you're shifting down pi over 3 units. And so basically you just take each point and you move it down pi over 3. So from pi over 2 here, we go down a little bit. And I don't even know what that is, so I'll label that in a minute. This one goes down a little bit too. And this one goes down a little bit also. And then I get my corresponding graph, which is supposed to have the shape, basically. And how do you find those points? Well, the inputs don't change. So that's still 2. But pi over 2 moves down pi over 3. So over here, let's just do pi over 2 minus pi over 3 and see what we get. Of course, you need to find a common denominator here. So you multiply top and bottom by 3, and you multiply this top and bottom by 2. And so you get 3 pi over 6 minus 2 pi over 6, which is just pi over 6. So this is pi over 6. This point's a lot easier to find because you're starting from 2, 0. So you go 2 and then down, so minus pi over 3. And then this one right here, it starts here at 1, so it's still at 1. And then you move down from negative pi over 2, you move down pi over 3 more. So what is that? So again, I need to use a little side here. It says negative pi over 2, and we take off pi over 3. Find a common denominator, so you multiply top and bottom by 3 here, and you get negative 3 pi over 6, minus, multiply top and bottom by 2 here, you get 2 pi over 6. And so what does that equal to? Minus 3 minus 2 is minus 5 pi over 6. And so this is negative 5 pi over 6. And so there's my final graph. You know, as long as you label the points, you're good. On the test, I might actually give you sort of a diagram, you know, more of a coordinate system to kind of fill in, so it's not so open, because it's hard to do these when they're open. Now I can say something like, hey, what's the domain and what's the range? So for the domain on this function, this new function, remember, how do you find it? Well, it's just the input values. So notice, you know, you're just going from here from 1, and you include the endpoint because it's a closed circle, all the way out to this point right here, which is 2. So this goes from 0 to 2. And then the range, what is that? Remember, those are the output values. So you come down here, and then the output value, you start right here, is negative 5 pi over 6. And then you go all the way up to right about here, which is that output value, which is pi over 6. And so it's all that stuff. So you have negative 5 pi over 6, comma, to pi over 6. And you include those endpoints because, again, these are closed circles right here. There should be a parenthesis right there. Let's do that in blue. Okay, there we go. So there's our domain and our range. And you can check your work, right? So it's not that hard to check your work on your calculator. So if you have the correct answer down, all you have to do is take your calculator, hit y equals, let's just graph this thing. So hit clear and then hit second sign. And then you have an x minus 2 in parentheses, and then you're going to take off that pi over 3. So say raised to divide by 3. Now here's where it's tricky. You got to make your window. So if you make your window and use the numbers here, like negative 5 pi over 6, you know, up to pi over 2, you can kind of get a good feel for what this is going to look like, right? So here, my calculator's off the screen. So for x min and x max, I'm going to go from negative 1 out to 2. I'm going to change my scales back to 1. And then for y min and y max, I'm actually going to go from negative 5 pi divided by 3. And I'll go up to pi over 2. That's fine with me. Second pi, oops. So second pi divided by 2. And then if you hit the graph, you should see we get the same sort of graph we got over here, right? Oops, I might have made a mistake here when I plugged this in. So let's make sure I plugged in the right thing right here. So this should be, I think I forgot to divide this by 6, guys. So that should be what? Let's see, negative 5, and then pi, and then divide by 6. There we go. Now hit the graph button. It looks much better, right? It just didn't look right. And so I have that there. And uh-oh, I see I made a mistake. Aha, and I did make a mistake. So you probably caught my mistake. So notice when I was counting over, I'm off a little bit. So I can see on my graph that I'm off. So I need to fix this. I can see that I'm off and I see where my mistake is now. When I did this horizontal shift, and maybe you caught this, so go back and fix this, and let's do our fix. We'll fix it in, let's fix it in pink. So I'm going to fix this in pink here. So right here, this should be a 3. Right? That should be a 3 because that's a horizontal shift over 2. So 1, 2, 3. And so this should be a 3. So I just mislabeled these points here. And so this should be then a 3 because it changes our domain also too, right? So this should be a 3 right there. Right, that's kind of funny, right? You can see it's a mistake because that's a 2 and that they're not both 2s, right? So checking your work is really beneficial. It's easy to make mistakes. So let's check it again now. Make my window go from -1 to 3. And you'll see now I got it. Now I get the whole thing. There it is. Right? So now I got it. Right? So you can kind of check and see how it's the same. I mean, you can even, for fun, if you want to graph the original sine inverse on here, right? So sine inverse of x, and hit the graph button, and then you get kind of some perspective of what's happening. So you can kind of see how it shifted over 2 units and then shifted down pi over 3 units. So always check your work if you can. Right? It's super easy to make mistakes. But of course, if you show your work, you'll minimize any sort of losses. All right, guys. So I just came back from lunch, and I realized that there's a mistake. So I don't know what happened, but when I said 1, but I put 0 there, so that should certainly not be 0. That should be the number 1. So let's go back here because like I said, it is super easy to make mistakes on here. So notice the domain, I said this right, it goes from 1, and then I corrected it to 3 right here. So my domain goes from 1 to 3. So make sure you make that correction. Otherwise, of course, it's incorrect. All right. So moving on to the next problem. All right, so we got to do some of these trig inverse stuff by hand. So let's do this. And when we do these types of problems, we're going to have to use our reference table probably. So, but I'll do that. We'll get to that in a minute. So how do we find tan inverse of negative square root of 3 by hand? Now, remember, on the calculator, I know the answer. So it's kind of nice. You can have the calculator kind of up and running. So if I hit second, let's put out here, second tan, and then type in, negative square root of 3, so square root and 3, kick it out in parentheses, it's going to tell me what the answer is. So the answer is that, whatever that number might be, right? And so now I got to go find why it is that number. So the trick here, the key to understanding inverse trig functions is to remember tan inverse of negative root 3 isn't just anything, it's an angle. So it gives you some number, and that number is not just any number, it's an angle. And as soon as I write that, I'm pretty sure I can solve this problem, because then I can tan both sides. So I'll tan the left and tan the right. And the tan always goes on the left-hand side of the object, the expression. And tan and tan inverse, they undo each other. So I just get negative root 3 on the left equal to tan of theta. And as soon as I have that, I know I'm solving basically a trig equation, but a very special trig equation that has only one solution. So I come over here and I do all students take calculus. And I'm going to go find the angle. And so the tan of the angle is negative. So I know I can't live here or there. So I'm not in the first or third quadrant, because when you take angles in those two quadrants, you take the tan of it, they're positive. So you have two choices, either here or there. And you're going to decide which choice you're going to go with. And what I usually tell you guys is, remember, over here, this is the abyss. So you never want to go by it, although it doesn't really come into play on this problem. So you never want to go over here, basically. But the idea is how you want to get to the angle as quick as possible from this axis right here. So where's the closest quadrant? Well, that would be this one, right? So if you're right here, you want the closest one. So it'd be right there. And so that's where your angle theta lives. We need to find this reference angle here. And there are a couple of ways to do this, but remember, you're not allowed to use your calculator. So it's like, well, that's what I would normally use here to find that reference angle, but I can't because I'm not supposed to use my calculator. So what I need is the reference table to help me. So over here, let's write the reference table. So remember, you have these standard reference angles, 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And we can write these in degrees and also radians. So 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. Let's make that 3 a little bit better. And then down here, we can figure out the sine of theta and the cosine of theta if we know this pattern. So remember, the sine of 0 is 0. So it goes root 0, root 1, root 2, root 3, and then root 4. And then these are all divided by 2's. Now what's nice about this pattern is it simply repeats for the cosine of theta, but going the other way. So it goes root 4, root 3, root 2, root 1, and then square root of 0. And these are all divided by 2's. And then some of these, of course, are going to simplify a little bit. So, of course, that one's equal to 0. That one's equal to 1. That one's equal to 1/2. Down here, that's equal to 0, and that's equal to 1/2. And so this reference table are basically the sines and cosines of the angles that we should know, in a sense. And so now we're dealing with the tans. We have to make that third line here. So remember, we don't normally do this, but we can do it. So the tan of an angle is just a sine divided by the cosine. So 0 over 1 is 0. 1/2 divided by root 3 over 2. Now this one's a little bit tricky, right? But if multiplied by the reciprocal, and you get 1 over root 3, because the 2's are going to cancel. And then you have to rationalize the denominators, usually the form that's given to us. So that one's root 3 over 3. This one's super easy, right? So root 2 over 2 divided by root 2 over 2 is 1. Root 3 over 2 divided by 1/2. The 2's cancel, you just get root 3. And then this one, remember that's supposed to be a 1 there. 1 divided by 0 is undefined. All right, so notice this is a square root of 3. And notice this is square root of 3 on the tan line. And so the reference angle has to be pi over 3. And so on my picture, I'll draw my reference angle to be pi divided by 3. And once I do that, I can read off my answer. So remember, you always start on the x-axis. And to get to that angle, you can't go through the abyss, remember, so you don't want to do it in standard position. Otherwise, you have to go through the abyss. So you just move down. And when you move down, it's negative pi over 3. And so theta should be equal to negative pi over 3. And so that should be your answer. And just make that 3 a little bit better. And you can check it on your calculator. So that number you found on your calculator, what was it? It was this number right here. And let's just see, is that negative? So negative second raised to, there's the pi divided by 3. And you see, oh yeah, those two numbers are indeed exactly the same. All right, so that answer to that, tan inverse of negative square root of 3 is indeed negative pi over 3. All right, let's move on to the next one. So in the next one, what do we have? We have cosine of sine inverse of negative 5 divided by 13. What is it equal to? And so, again, when I look at this, my brain always gets stuck. It's like, what do you mean? I don't even understand that thing. Oh, hold on. Let me slow myself down here. That's sine inverse. Remember, if you sine inverse of something, you don't just get anything. You get an angle. So that's like cosine of theta. where theta is equal to that sine inverse of -5/13. And as soon as I do that, I'm like, I got a shot at solving this because I know how to get rid of sine inverse. I'm going to sine both sides. And then I can just find out what cosine of that angle is by doing all students take calculus. So now I'll just sine both sides. So sine this side and sine that side, always on the left. And I get sine of theta is equal to, and sine and sine inverse, they undo each other. I get -5/13. And so again, I'm going to solve a trigonometric equation in a sense, but I don't have to go all the way on it. So I'm going to do all students take calculus, try to figure out where theta lives. And remember, theta is very special. There's just one angle because you started with this sine inverse. So you just get one answer out here. And in fact, you could probably use your calculator to tell you where that answer lives if you wanted to. Of course, we're doing everything without a calculator here except to check our work. All right, so what we got? We have sine of theta equals -5/13. So it's negative, so I know I can't live here and here. So I got two choices, the third or fourth quadrant. And each of those choices are good, but because you're working with the inverse trig function up here, remember, this is the abyss. So you're never in here when you're working with inverse trig stuff, at least when you start with it. So my angle must be in the fourth quadrant. So let's draw it here. So there's my angle. I need to find, well, normally I need to find the reference angle, but this time, what am I looking for? Excuse me, I was going to sneeze. I'm just looking for cosine of theta. So actually, all I need is my right triangle. So I'm going to make my little right triangle here. So I don't really need to find the reference angle. I just need to make my right triangle and find the sides. So I'm going to do SOHCAHTOA. And so if I can find the sides of that right triangle, then I can tell you what the cosine of theta is. All right, so what are the sides of the triangle? Because I am using the sine here, I'm going to use the SO. And so I have the opposite over the hypotenuse. And so the opposite is -5. And it's clear it is negative because it's going down. And then the hypotenuse is +13. So there's 13. And of course, I'm missing this side right here, but that's not that big of a deal because I can just use Pythagorean theorem to find it. So the Pythagorean theorem tells me what? It tells me that a squared plus b squared is equal to c squared. And so I don't know what a is, so I just write down a, so a squared plus, and then I have -5 squared is equal to 13 squared. And so a squared plus 25, the negative goes away, and then equals 169. And so then I know a squared is going to be equal to 169 minus 25 is 144. And so take the square root of both sides, and I notice a should be positive. So when you take the square root, you just want the positive piece. And so a is going to equal +12. And you can use your calculator to find square roots or squares if you want to. That's allowed on the exam. So make sure you show your work. And so a is equal to 12. And now I got it. So to find the cosine of theta, I use the CA, which is the adjacent over the hypotenuse. So it should be 12/13. And so now I want to check my work with my calculator. So on my calculator, I'm just going to plug this in here. I'm going to plug in this cosine. I guess I have to keep it over here because I can't pull it up on my screen large enough. But I'm going to plug in cosine of second sine. And then that was what? -5 divided by 13. In parentheses, hit enter. And out pops this number, and I'm like, I hope that's 12/13. Because if it is, I did it right. If I didn't, I have to go back and see where I made a mistake. And it is. It's exactly the same. So check, I did it right. So over here, check off the problem, right? So 3 is good to go. Oh, and back at 2, you could check that problem off. Oh, I guess I just did B though. Let's just do B, right? That one's good. That one's good. So we just checked off A, checked off B. All right, let's move on. So down to C here. Now, notice, let me move that back up a little. C is kind of similar to B, but it's actually a little bit easier. So we're going to use a right triangle to solve this, but our right triangle is kind of idealized. We're going to take the best case scenario, which means you're always in the first quadrant. And that's an assumption we make on this problem. And so we want to find the tan of cosine inverse of x over 4. So what does that equal to? And again, I look at this and my brain always gets stuck until it's like, oh, I know you. You're not just anything. When you take the cosine inverse of something, you get back an angle. So you're tan of an angle. So theta, where theta is equal to that cosine inverse of x over 4. And so now what I can do is I can cosine both sides. So cosine the left and cosine the right. And I get cosine of theta is equal to x over 4. Because cosine and cosine inverse, they undo each other and leave you with the input you started with. And so now again, it's like, oh, I'm solving a trigonometric equation, but I really don't need to do all students take calculus. But if you want to, you can. It doesn't hurt just to write it, but just realize, how do you pick the quadrant? You always take the easiest quadrant for this type of problem. So it's an idealized problem. So you're always in the first quadrant. I will always assume x is positive, basically. Okay, so let's just draw our triangle. Right, so our triangle is right here. This is our theta. We use SOHCAHTOA. Right, we use SOHCAHTOA to find this. So this is the ka we're going to use because I gave you the cosine of the angle here. And so this must be the adjacent. This must be the hypotenuse. And so the adjacent's right here. It's always the input. And the hypotenuse, of course, is the long side here. And so that's the 4. And of course, we're missing one side. We'll call that side B. And we need to find B because remember, at the end of the day, what are we looking for? Just the tan of the angle. And so we'll use that Pythagorean theorem again. So let's just write out Pythagorean theorem, which says a squared plus b squared equals c squared. And it's just basically plug and chugging a little bit. So here, a is x, so we write x squared. B we don't know, so we just write b squared is equal to, and c is 4, so 4 squared. And so x squared plus b squared is equal to 16. And so b squared is equal to 16, well, minus x squared up on both sides, so subtract x squared on both sides. So it cancels on this side. And so we're just taking off x squared on this side and on this side too. And so, of course, we get b squared by itself and 16 minus x squared. And now here, we're going to take the square root of both sides. And notice, b is certainly positive. It's idealized, so it's always going to be positive in this situation. So b is equal to the square root of 16 minus x squared. And so my b is equal to the square root of 16 minus x squared. And now I got it. To find the tan of the angle, it's the TOA. It's the opposite over the adjacent. So it's going to be equal to the square root of 16 minus x squared, all divided by the adjacent, which is x. So that's my answer. And on this one, you can check your work too, but you have to kind of be careful about what numbers you plug in for x. But the idea is let's just plug in 1 here and see what happens. So on my calculator, I can take this and type in, I really want to see the expression because I don't have it memorized right in front of me here. So here I can type in tan of second cosine, there's cosine inverse, and then type in a 1 for x. So 1 divided by 4. And I probably get out a pretty crazy looking number. Let's see. Yeah, pretty crazy. And the question is that number the same if you plug it in 1 into here? Do the same number back basically. So second square root, and then I have 16 minus 1 squared, which is just 1, but I'll type it all in. And then kick it out, and then of course divide by 1 and see what you get. And notice the numbers are exactly the same, right? Because they're the same, we can just check it off because that's definitely right. So that's kind of nice. All right, last problem here to do by hand, at least last problem for number 3. is we want to find the sine of negative 15. And we have to do this by hand. So if it means we're doing it by hand, it means we're using the reference table. So let's go back up here. And I'm going to snip that reference table and bring it down here. So we move up here. Let's grab that reference table. I'm just going to snip it and bring it down to where I want it to be. And let's bring it down here. So down here, for this problem. So we can just kind of look at it. You can see the idea. And so notice there's no 15 in this reference table. So we're kind of like out of luck to begin with, but there are ways to make a 15. There are a couple ways to make a 15 actually. I'm going to make a 15. I think the easiest way is just by using a 30 and a 45. I think that's the easiest way to make 15. And I want to make negative 15. So notice this is the same thing as sine of 30 minus 45 degrees. Because 30 minus 45 is negative 15. And if I use that in the sense that that's the sine of the difference of two angles, I can use my formulas. So that's the same thing as equal to. Remember, sine has the same sign, so it's a minus here. And something's always different, right? Sine has the same sign, but something's always different. So it goes sine, cosine. So it's sine of 30, cosine of 45, and then sine 45, and then cosine of 30. Sweet. So now I can just plug in. So I need a sine of 30 and a sine of 45, which I have that. It's right here. So 1/2 and a root 2 over 2. So here I'll put a 1/2. And here I'll put a root 2 over 2. And in between, of course, I have a minus here. And then I also need a cosine of 45 and a cosine of 30. Well, I got that too. Right? Cosine of 30 is root 3 over 2. And cosine of 45 is a root 2 over 2. So here I put root 2 over 2 for cosine of 45. And here for cosine of 30, I put root 3 over 2. And now the rest is just some arithmetic. So I multiply 1 times root 2 is root 2, divided by 2 times 2 is 4, minus root 2 times root 3 is root 6, and 2 times 2 is 4. And so I get root 2 minus root 6, all divided by 4 as my answer. And of course, I can check it easily with my calculator. So on my calculator, I can take the sine of negative 15. Just have to come back up over here and hit negative and 15. And then hit enter. And I get out that crazy number. And I just wonder, is that the same as this expression I got here? So let's type that in. Left parenthesis, second square root of 2, kick it out, minus second square root of 6, kick it out, in parenthesis, divide by 4. If they're the same, I'm good to go. Uh-oh, they're not the same. So what could be the problem? If they're not the same, I mean, it's definitely negative 15. We have to remember, what's the common mistake when you're plugging in angles? So think for a second, because I actually have the right answer. But guess what? Hit mode, and I'm in radian mode. Crap, I got to go down here, change it to degree mode. So let's hit enter on that. Second quit, so now I'm in degree mode. I'm going to hit second entry, and then second entry one more time to pull up the last expression. So that's sine of negative 15. Now hit that again, and notice, yes, they are exactly the same, right? So be careful. It's easy to put yourself in that wrong mode. So that looks good. So I was just in radian mode. I should have been in degree mode. All right, let's move on to some more problems here. So we have solving trigonometric equations. So these are always good problems. And it says use reference angles to solve for each equation for x. And so that means we have to use reference angles. But basically, you have to draw the picture. And so down here, I'm actually going to bring back that reference table again, because when you solve these, sometimes you can use the reference table and sometimes you can't. So look at the reference table actually right down here. All right, so how do we solve this equation? Sine of x equal to negative 2 over 5. So first, notice negative 2 over 5 is not in your reference table. So you're probably not going to be able to use it. But you can still solve this by doing all students take calculus and finding the reference angle, because it still has a reference angle. It's just not one of the standard ones, which means it's not a 0, 30, 45, 60, or 90 degree angle. So all students take calculus. And I know the sine of the angle is negative. So I know I can't live here and I can't live here. So I live in this quadrant or that quadrant. I draw both the angles because you're going to get lots of answers here. So notice your answers aren't limited. The next problem, you do limit your answers a little bit between 0 and 2 pi. But up here, there's no limit. So you're going to get an infinite number of answers. And so now I need to find my reference angle here and here. And notice it's not in my reference table because negative 2 over 5 isn't in there. So what can I do? Well, you can sine inverse both sides and see if you do get back a reference angle. So I'll sine inverse this side and I'll sine inverse that side. And so sine inverse of sine of x, it's just x, they undo each other. And then this is equal to sine inverse of negative 2 over 5. And so the question is that a reference angle? And so to check that on my calculator, what I like to do is just make sure you're in degree mode for this, because we're going to interpret what sine inverse of negative 2/5 is. So I'm going to type in second sine inverse of negative 2 over 5. And what you'll see is that it's not positive, it's negative. So it's not a reference angle, but you can make it a reference angle. So what it's giving you is the angle from here down to there. But we'll just make it positive. So how can we make it positive? We can just add a negative sign in front of it. So what we'll do is we'll write this as negative sine inverse of negative 2/5. Because we want our reference angle to be positive. You don't want to have direction because you're basically going to add or subtract it depending where it lies on your picture. And over here, same thing, negative sine inverse of negative 2 over 5. And now I can start reading off my answers. So my first answer, and to be honest with you guys, there are lots of ways to write this down. So I think I'm going to take the easy way out of here, right? Because it doesn't restrict me. So my first answer, I might just be like, oh, from here to there, which, what is that angle? The idea is you go halfway around and then you add negative sine inverse of negative 2/5 to it. So if you add negative, it's really subtract sine inverse of negative 2/5. And so that would be my first answer. So x is going to equal pi, remember it is x because you have an x in here. And so pi minus sine inverse of negative 2/5. And then you have to add that plus 2 pi n. N is an integer. So there's my first answer. And then my second answer, if you want, I can go all the way around to here, but there's no restriction on my answer. So I can just start here and go back if you want. So when you go back, you basically just subtract off the reference angle. So minus a minus is a positive sine inverse of negative 2/5. And so my second answer will be equal to, so x equals sine inverse of negative 2/5. And I can just add 2 pi into it. Again, you can wrap all the way around and get back to another answer. So 2 pi n is an integer because it doesn't matter which way you wrap around, clockwise or counterclockwise, you still get another answer at that angle. And so you have two sets of angles there. And that's the answers. All right, let's do the next one, because the next one, you don't get an infinite number of answers, you're going to get a finite, because we're going to be working on just 0 to 2 pi. And so we want to solve this trigonometric equation here. Now, this one, remember the big idea. The big idea is we want to get this to look like the sine of something equal to a number, the cosine of something equal to a number, or the third case is the tan of something equal to a number. If we can do that, we can basically do what we just did before in a way, and then do all students take calculus and find our answer. So notice we're not in one of these three situations. Definitely not. But we're close to being in it because this reminds me of one of those formulas. It reminds me of one of those sum and difference formulas. So notice the difference is sine cosine. So here the sine is the same. So when the sine is the same, you have a sine, and then this is probably your alpha, and that's your beta. So this is sine of 4x minus x, and you can kind of check it. So remember, sine has the same sign, so there's a minus, but something's always different. Well, that's a sine cosine. So that checks, and that's equal to root 2 over 2. And so what we get here is sine of 3x equal to root 2 over 2. And so now we're basically in the same situation we are before. We're actually a little bit better. But we can do the same thing. So over here, let's draw all students take calculus now. So all students take calculus. I can find where the angle lives. So the sine of the angle is positive, so I must be either in the first or second quadrant, because down here the signs of angles are negative. So draw the angle. And of course, we're looking for the reference angle here and here. And so now how do we find the reference angle? Well, this is a nice number in our reference table. So you come over the sine line, you find that number, and you see the reference angle is pi over 4. So this time you don't have to sine inverse both sides. It's not wrong if you do, but remember at the end of the day, you do have to write down the exact answer if we know it, right? So sine inverse of root 2 over 2 is pi over 4. Once you write down the reference angle, we're ready to read off our answers. So here's my first answer right here. And so my first answer is 3x, because remember, our angle is not x now. The angle is 3x. And so that first answer is just pi over 4. And because we have that 3 there, we do have to add on that 2 pi n. It is an integer. Even though we're only going to get a finite number of answers because we're focusing on between 0 and 2 pi, so we're just focusing on a full revolution, one revolution, we will need to find those answers by counting them off, basically. And then the second set of answers, 3x is equal to, it starts here and goes right there. So to find that one, the idea is go halfway around pi and go back pi over 4. So that angle is really go halfway around and then go back the reference angle, pi over 4. So it's like go all the way around and then go back and you get to that angle. And so that's going to be equal to, if you find a common denominator, that's going to be 4 pi over 4 minus pi over 4. So that's going to be 3 pi over 4. So this one is 3 pi over 4 plus 2 pi n. N is an element of the integers. Okay, I'm ready now to solve for x. So I'm going to multiply both sides here by 1/3, both sides here by 1/3. And notice the 3, of course, will go away because 1/3 times 3 is 1. So I just get an x. 1/3 times this, that's just pi over 12. You just multiply the denominators. So 3 times 4 and 1 times pi is pi. And then if you multiply this by 1/3, you get plus 2 pi n over 3. And n is still an integer. Same thing here. Multiply that by 1/3, you get x. Then you multiply this by 1/3. The 3's cancel. But I'm going to keep the denominators the same because at the end, I have to count off a lot of these because it's 3x. So I probably would just keep these the same. So I'd probably keep this as 3 pi over 12. If you cancel, it's not that big of a deal, but I'll have to reinstate it later. So then I multiply this by 1/3, and I get 2 pi n divided by 3. And let's make that 3 a little bit better. And n is still an integer. Okay, so what I just found are all the possible solutions to this equation. Right here, where when you plug in x, you get out root 2 over 2. But of course, I don't want all of them. What do I want? I just want the ones between 0 and 2 pi. So now I have to count them off. So let's count them off. And so when I count them off, you always start at 0 because the way this technique works, the way the method was created, it's basically you start at 0 and you always get the first answer. And so on here, I have x equals, I'll just write down n equals 0 so you can see what I'm plugging in. So when n is equal to 0, notice what happens. That term goes away and you just get pi over 12. When n equals 1, this term doesn't go away. You just get 2 pi over 3 because n is 1. So you add 2 pi over 3 to pi over 12. I can't do that. I don't have a common denominator. So I need common denominators first. So let's make common denominators here. So to kind of fix this, I'm going to give myself a little more space. So I need a common denominator to kind of work with this thing. So that's equal to, of course, pi over 12. And then plus you multiply top and bottom by 4. You get 8 pi n over 12. Now it's easy to kind of let n be 1. So you just add 8 pi over 12 to pi over 12. You get 9 pi over 12. And then when n is equal to 2, you add 8 pi over 12 again and see what happens. So 9 pi plus 8 pi is 17 pi over 12. And so there's your second answer. Now what happens though is if n is equal to 3, what happens here is you get 24 pi over 12, which is 2 pi. So you're adding 2 pi, which is too big. And of course, if n is negative 1, so if you think, well, maybe I should work backwards too, which is not a bad idea. But if n is negative 1, you get minus 8 pi over 12. If you add pi over 12 to minus 8 pi over 12, it's negative, which that's too small. You have to stop at 0. So it's outside the 0 and 2 pi bounds, basically. So those are your 3 answers. And so now we repeat this process over here. You have 3 pi over 12. We're going to common denominator. So plus, multiply top and bottom by 4s, and you get 8 pi n over 12. And so our first answer is x equals, and again, you start with n equals 0. When n equals 0, this term just goes away. Anything times 0 is 0, but you do get 3 pi over 12. So it's 3 pi over 12. And then when n equals 1, you're going to add one of these because n is 1. So add 1 8 pi over 12 to 3 pi over 12, and you get 11 pi over 12. And then when n is equal to 2, right, you add another 8 pi over 12 because it's 2 times that. So you add one more 8 pi over 12 to 11 pi over 12, and you get 19 pi over 12. And that will be our last answer. That one. And you can leave it like that. If you realize you can simplify some of these, that's great. So feel free to simplify. Like this one can be simplified to 3 pi over 4. 3's cancel on top and bottom. And this one can also be simplified to pi over 4. But if you don't see that, it's not a huge deal to me. Right? What's the huge deal is you can get all those possible answers, right? Because that's not an easy problem to solve, basically. And we can then check our work on this if you want. So let's do that, because I have made several mistakes so far on this review, and by checking my work, I found them. So let's check our work by using that number right there. So that's 19 pi over 12. So if I did this right, I should be able to plug this in to my original equation over here and get out root 2 over 2. So let's do that. And so to do that, I wonder if I can, I guess that's good enough. So I'm going to turn this on, and then I'm going to type in, make sure you're in radians. That's important. So make sure we're in radians. So hit enter on radians. And then let me get that answer on the screen. So there it is. And so I'm going to type in the sine of 4 times 19 pi. Well, this is going to be a pain to type in, but whatever. So 19 pi divided by 12 in parentheses, and then the cosine of 19 pi over 12 in parentheses, and then minus the sine of, not a 4, but a 19 pi over 12 again. And then in parentheses, cosine of 4 times 19 pi over 12. In parentheses, and then hit enter with your fingers crossed, and now pops that number. I'm like, oh, is that root 2 over 2? I don't know. Let's check it. Second square root of 2, kick it out, divide by 2, and it is. So I'm pretty sure I did this right, so now I can check that one off if you want right here, because those 2 answers were exactly the same. All right, so there's solving trigonometric equations. And now we move on to our final problems here. So I guess we have 2 more, 5, 6, and 7 left to do. So let's do it. So on number 5, we want to find tan of alpha plus beta and tan of 2 beta. And they give us a bunch of crazy information, right? So before I do that crazy information, I can kind of just separate this out and say, okay, so tan of alpha plus beta is equal to the sine of alpha plus beta divided by the cosine of alpha plus beta. And that's equal to, so I have these sum and difference formulas I can use. So sine has the same sign, so it's plus, but something's different. So it's the sine of alpha, the cosine of beta, the sine of beta, and the cosine of alpha. And then down here, it's exactly the same idea, but remember the cosine has a different sign, so it's plus, it's minus, but something's always the same. So cosine alpha, cosine beta, sine alpha, sine beta. And so my job is to find each of those sine alpha, sine betas, and then plug in and get the answer. Now, simultaneously, I think for fun, I'm going to do tan of 2 beta 2, because that's exactly the same idea. So notice part B, it says find tan of 2 times beta. So it's tan of 2 times an angle. So to do that, my brain's like, I can't work with tan. So I'll convert to sines and cosines. So that's sine of 2 beta divided by cosine of 2 beta. And then my brain's like, oh, I have formulas for this. These are double angle formulas. So I know this one is 2 sine of beta, cosine of beta. Whereas the bottom one, it's kind of like the Pythagorean identity, but with a minus, right? So it's like, oh, cosine squared beta minus sine squared beta. So you basically just reduce these to the sines and cosines of individual angles. We'll find those by using, all students take calculus, although this one they kind of tell you where the angles live. But then we'll use Pythagorean Theorem to solve the right triangles, and boom, we'll have our answer. So over here, all right, all students take calculus, even though I don't need it. It's always good just to write it. And I'll start with my first thing here. So it says cosine of alpha equals 12 over 3 alphas in the first quadrant. So they need all students take calculus because it tells me alpha is right here in the first quadrant. And so then I can use SOHCAHTOA to label that triangle. So SOHCAHTOA. And here I'm going to use the CA because they give me the cosine of the angle. And so 12 must be the adjacent, whereas 13 must be the hypotenuse. So here's 12, here's 13, and I don't know that side. But I can find that side with the what? The Pythagorean theorem, of course. So I'm going to just move this over and then write down the Pythagorean theorem. So I'll use the Pythagorean theorem. To find my answer. Remember, Pythagorean theorem says a squared plus b squared equals c squared. And so my a is 12. My b, I don't know. So b squared is equal to 13 squared. And so you can use a calculator to find these numbers. So it's 144 plus b squared equals 169. If you subtract these two things, you get b squared equal to 25. And so then take the square root of both sides, and it is positive, so b is equal to 5. So b is equal to 5. And now I got it. So I know what cosine of alpha is, and I know what sine of alpha is. So cosine of alpha should be 12 over 13. It's the CA. And sine of alpha should be the opposite of the hypotenuse. It's the SO. So it's 5 over 13. And so basically what I can do now is I can plug in for any sines or cosines of alpha. So all this stuff I can plug in for. But the sine and cosine of beta I still have left over. So I still have to do that. So I'm going to come back over here and do what I just did before again. But this time I'm going to do it with this stuff. And so beta lies in the second quadrant. So it's over here. So I can draw beta. So there's beta. It has a right triangle. So you have kind of an alpha triangle and a beta triangle. I can find the sides of my triangle with the SO because it's a sine of beta. So that must be the opposite on top and the hypotenuse on the bottom. So here's the opposite side 3. The hypotenuse is 5. And I need to find this side. And I'll do that with the Pythagorean theorem again. So Pythagorean theorem says a squared plus b squared equals c squared. But in this case, a squared plus my b is 3, so 3 squared, is equal to my c squared, which is 5 squared. And so a squared plus 9 is equal to 25. Subtract 9 from both sides. A squared is equal to 16. And now here's where it gets a little bit tricky. When you take the square root of both sides, a is in that second quadrant. So when you take the square root, you don't want the positive, you want the negative. So a is going to be equal to negative, the square root of 16 is 4. And so that's equal to negative 4. And so now I have it. What's the cosine of alpha? Well, it's the adjacent over the hypotenuse, negative 4 over 5. And for fun, I can write down the sine of alpha, even though they already gave it to me, but you can see from the triangle, it's 3 over 5, which is exactly what I was given. And so now I can come back over here and I just plug in. So notice I can just plug in for cosines of betas and sines of betas. Right? So let's just do that and we can color code it for fun. And so this will be equal to, so remember sine of alpha was 5/3. So I put a 5/3 here. And then cosine of beta, where's cosine of beta? It's right. Ooh, I wrote down the wrong lettering here, guys. So let's fix that because that's important. In fact, let me just erase it right here. So I think it's important enough to make sure that the lettering is correct, right? So in your solution, make sure you have beta there, not alpha, because that's certainly beta. And so the cosine of beta is equal to negative 4 over 5. So negative 4/5. And then we have a plus, and then the sine of beta, that's right here. So that's 3/5. So we put a 3/5 here. And then a cosine of alpha. Well, where's cosine of alpha? That's 12 over 3. Just read it off. Or 12 over 13, sorry. And then divided by, we get cosine of alpha again, that's 12 over 13. So 12 over 13. And then times cosine of beta, which is negative 4 over 5. And then minus a sine of alpha. Well, where the heck is sine of alpha? Ah, it's 5 over 13. So 5 over 13. So notice up here, sure that 5 over, I put a 3 there. It should be a 13, right? So that'll screw me up if I leave that. So 5 over 13, and you can see like these reds kind of, and greens kind of help me keep track of information. So sine of beta is 3/5. So every place you'd have Christmas colors basically, right? So reds and greens next to each other. And so there we go. Now I have to do the arithmetic. It's a little bit painful, but we can do it. So 5 times negative 4 is negative 20. 13 times 5, I think that's 65, right? So it's like 5 times 10 is 50, 3 5s is 15, yeah, 65. And then plus 3 times 12 is 36, yeah, 36. And then down here, again, 5 times 13, 65. Oh, crap. I'm running out of space. So let's make some more space for myself here. So I'll take this and let's just move that down a little bit and make some more room right here. And so now let's go back up. We got some more space. This is divided by, and then down here, 12 times negative 4 is negative 48 over 65. And then minus 5 times 3 is 15 over 65. And so that's equal to negative 20 plus 36 is 16 over 65. Negative 48 minus 15. Oh, geez. Okay, so we got to be careful here. So that's negative 58, negative 63 over 65. Let's check that real fast. All right, so negative 55 and 3, yeah, we're good. And then you multiply by the reciprocal, so 16 over 65 times 65 over negative 63. And so the 65s cancel, and I get 16 divided by negative 63, which I think that's as far as we're going to be able to go, right? Because 63, negative 63, that's not going to go into anything nice, right? So I think that should be our final answer there. And this one is actually very hard to check work. So I usually don't check it. Like I said, it's super hard to actually check. So I would just leave it. And if you have a mistake on it, you'll probably catch it. I mean, it probably isn't a big mistake, so you don't really need to worry about it. So So I would just leave it alone, right, for now. All right, so my answer is negative 16 over 63. I really want to check it, guys. I'm going to show you how. I'm going to check it because I really do want to check it because it's so easy to make silly mistakes on this. And if I made a mistake, I do want to go back and find it eventually. So the way you check these can be pretty tricky. So make sure when you check this thing, make sure you're in degree mode. Otherwise, it's kind of tough to check. So I'm going to put myself in degree mode. And what you do is you simply just come up here and you want to find the different angles. So I want to find alpha, right? How do you find alpha? Well, you take cosine inverse of both sides. So I'm going to hit second cosine and do 12 over 13. And I'll see what alpha is. And so there's alpha. And it's in the first quadrant. So I'm good to go. So that's great. That's alpha. And it's in the first quadrant, 22 degrees in the first quadrant. And then for beta, let's see what that is. So second sine inverse of 3 over 5. Now, this one will probably not be in the second quadrant. I think it's in the first. Yeah, it's in the first quadrant. So I have to put myself into the second quadrant. So it's really 180 minus that answer, right? So the idea is, you're in the first quadrant. Where do you get the sort of equivalent angle in the second quadrant? We have to take 180 minus that reference angle, and that puts you in that second quadrant right there. So when I check this, here's how I check it. I do the tan, and I do second cosine inverse, second cosine inverse of 12 over 13, because remember that was in the right spot, in parentheses, and then I would add 180, I gotta get up here to get to the 0, so 180, and then minus second sine inverse of 3 over 5, because that's that angle in the second quadrant. Then hit enter, and that's what I get out. And so I'm hoping, otherwise I have to go back and find my mistake, that negative 16 over 63 is that answer. You see this, right? Again, that one's super hard to check, but I want to check it because it's so easy to make mistakes on these, but that's the right answer. So 16 over negative 63. So boom, verified. All right, let's go down here because we basically have all the information we need for this one. What is a tan of 2 beta? So it's going to be 2 times, and then we just use what we found before. We already found the sine of beta. It was equal to 3 over 5. So 2 times 3/5. And then the cosine of beta, we found that too. That was equal to negative 4/5. So negative 4/5. And then divided by cosine of beta squared, so that's negative 4/5, quantity squared. And then minus sine of squared of beta, so that's 3/5, quantity squared. So we've already done all the work here in the problem before, right? So we don't really have much to do. And now it's just a bunch of arithmetic. So it's going to be equal to 3 times negative 4 is negative 12 times 2 is negative 24. Divided by 5 times 5, so that's 25. Then all divided by, from the bottom here, the negatives go away because you're squaring them out. So it's 16 over 25 minus 9 over 25, which equals what? So negative 24 over 25. All divided by 16 minus 9, go down 6, down 3, that's a 7 over 25. And so that's equal to negative 24 over 25 times 25 over 7. So you multiply by the reciprocal, boom, boom, those go away, and we get negative 24 over 7. And remember, we can check this one too by simply going back to our calculator. Remember, when we did this sine inverse, that was beta, basically, right? With that sine inverse, we were in the wrong quadrant, so we had to do 180 minus it. So I'll do tan of 2 times, and then in parentheses, 180 minus second sine inverse. This is just me checking my work of 3 over 5. 5. In parentheses, hit enter. I get out this crazy number here. I'm like, is that negative 24 over 7? Let's see, negative 24 divided by 7, and boom. It is. All right, so we're good to go. Thank you. All right, check. All right? So it's nice if you can check those. But those are hard to check. So I usually tell you guys, if you have problems checking it, I understand, right? Just leave your work on there. And if you made a silly mistake, I'll try to minimize the loss there. All right, so we're almost done. We have 6 and 7 left to do. Okay, so number 6, we want to use the triangle to answer each part below. And we can use a calculator to round any lengths to 1 decimal places and angles to the nearest degree. So let's do this. And of course, this is the law of sines and cosines problem because we haven't done that yet. So how do you find side A? So to find side A, we're going to use the law of cosines. You may ask, why aren't you going to use the law of sines? I'll say you can't use the law of sines. No matter how hard you try, you won't be able to use the law of sines on this. And remember, this is not a right triangle. If you try to use the Pythagorean theorem on this, it will be incorrect. So what's the law of cosines say? It says, and notice we want to find A, so we're going to use the version A squared equal to B squared plus C squared minus 2BC cosine of angle A. And we just plug in, we don't know what A is, so we have A squared equals, and always write down what you're plugging in. So 6 squared plus 11 squared minus 2 times 6 times 11, and the cosine of 45. Once you write down what you're plugging in, you can use your calculator to kind of crunch this number, but you might want to show a little bit of work. So here, what do we have? We have 6 squared plus 11 squared minus 2 times 6 times 11, and then cosine of 45. And then real quick, before you hit enter, right, so in that parenthesis, make sure you're in degree mode. So hit mode. I am in degree mode. Otherwise, your answer will be wrong. Then hit enter, and it spits out this number. And so what I tell you guys is just to kind of protect yourself, you may want to write this down to a couple decimal places. So write down A squared is equal to 63.66, and I didn't see what was after that, and 19 ... The ... just means that number is probably going to go on forever. There's no established pattern there, so it's probably going to go on to ever some sort of way. But at least I see what your calculator says. So if you put it in wrong, I can take off for that, but I don't have to take off for the next part, whereas to find A, you just square root both sides. And so A will be approximately to the nearest 1 decimal place. So on my calculator, I just hit second square root of that. So up here, this calculator got stuck. There it is. So second square root of that answer, and I hit enter. And so it's about 7.97, or I guess 1 decimal place, you round that 9 up to a 0 and you get 8. So 8.0. And so here you can write approximately 8.0. So that's how long that side is to 1 decimal place. Now we move on to find angle B. So to find angle B, now you can use the law of sines. And so on the law of sines to find angle B, we're going to do sine of angle B divided by little b, and then we have to find another side and angle to use. So since they give us this 45, we'll do the sine of angle A divided by little a. And we will use the approximated value for little a. So that's just fine with me. We'll just assume, we'll have some error in our solution, but it's not that big of a deal to me. So as long as you pick the right law to use, you can use the approximation. And so, here's our, each of these, here's our equation, and here we're solving basically. Here's our equation. And now we just need to write down, I'm going to keep it up here so you can see what I plug in. So here I'm going to write down sine of B divided by 6 is equal to the sine of 45 divided by 8. And then to get sine of B by itself, we'll multiply both sides by 6. So this side, the 6 goes away, and this side, we get what? So sine of B is equal to 6 times the sine of 45 divided by 8. And then to get B by itself, we'll sine inverse both sides. And so now we're basically solving here. And so sine inverse of sine is B. And so that's equal to sine inverse of, and then 6 over 8 cancel a little bit. So that's going to be a 3 sine of 45 divided by 4. And we'll approximate now with our calculator. We have the exact answer down. So algebraically, we're solid, basically. And now we'll use our calculator. It's in degree mode, remember, so that's what we want it in. So second sine inverse of 3, the sine of 45, in parentheses, divided by 4, in parentheses, hit enter, and out spits 32 degrees approximately. 32 degrees. So there's our answer for that one. Here's our answer for that one. So to the newest degree, 32 degrees. And so this one says angle to the nearest degree. And then finally, to find our last part, which is angle C, and I'm going to do that up here, guys, so we can kind of keep the picture on there. So to find C, you're going to find that angle there. Remember, if you add up all the angles, they add to 180 degrees. So show a little bit of work. So 180 is equal to C plus 45 plus 32. And again, you can use the rounded number. I'm fine with that. So 180 is equal to C plus, and that's 70 plus 7, so 77. So if you subtract 77 from both sides, you get 100 and, oops, we don't want that on there. Sorry, guys. So if you subtract 77 from both sides, you get 103 degrees is equal to C. So this should be 103 degrees. All right, and you can check it because the longest angle has the longest side, the shortest angle has the shortest side, and the middle angle has the middle side. So, I mean, it checks well enough. I'll take it. Doesn't mean it is right, but it's a good check, basically. All right, last problem, number 7, completely different than what we've been doing. Now we're going to solve systems of equations. And so this is kind of nice. And when you solve a systems of equations, remember, the long strategy, the one that takes a real long time, is, solve for x, then you can plug in, solve for y, then you can plug in and solve for z. But sometimes you can use symmetry of the system to make that go really fast. And so notice when I look at these equations, the way that they're written, these two have some things in common. They both have an x and y in common, right? X plus y. And so what that means is I can take advantage of that, in some sense, symmetry to simplify my solution. So what I'll do is, if I want to solve this really quick, is I'll just subtract these two equations. So I'll take x plus y plus 6x, or 6z, I'm sorry, equal to 26. And I'm going to take off x plus y plus 7z equal to 30. So I'm basically just going to subtract these two equations simultaneously. So it's like, take away the x's, they go away. Take away the y's, they go away. 6z minus 7z is a negative z. And 26 minus 30 is equal to negative 4. So in one fell swoop, multiply both sides by -1, I see z is equal to 4. So it's like magic, right? It's like if you use the symmetry of the system, if it has it, doesn't always have it, but if it does have some symmetry, some sameness, basically, you can utilize that and make your solution fall out pretty quickly. So now I know z is equal to 4. What I can do is I can plug it back into these equations. And so wherever I see a z, I'm going to put a 4. So I have x plus y plus 6 times 4. And let's just write that as 24. So 6 times 4 is 24, is equal to 26. And I can plug it into the second one too, but you'll see that you're actually going to get something out that's the same. But 7 times 4 is 28, which is equal to 30. And then I'll plug it into the last one. So x plus 4y minus 8 times 4, so minus 32, is equal to negative 21. And so I can simplify this system equations by moving the numbers over to the other side. So this implies x plus y is equal to, so move over the 24, so I get 2. Move over the 28, and you'll see you actually get exactly the same thing. So 30 minus 28 is 2 again. And then this one says x plus 4y is equal to, now we add 32 to both sides on this one. This one's a little trickier. So what do we get? We get x plus 4y, and then it should be a 32. And so negative 21 plus 32, what is that? Is that 11? It's positive 11, right? So if you take off 10, that's 22, another 10, that's 12. Yeah, positive 11. So notice These two are exactly the same. And that will always happen if you use two equations like we did up here to simplify. So you got to get a redundancy in information. So you just pick one. We'll take these two along with the third that we didn't use. And now we have a new system of equations just involving x's and y's. So x plus y is equal to 2 and x plus 4y is equal to 11. And so if you want, we can now subtract these, right? Subtract this one from the top one. So if you want, sometimes I put this in parentheses, but that minus goes all the way through. So x minus x, that gives you 0. So that's gone. Y plus a negative 4y is minus 3y is equal to, and a 2 minus 11 is a negative 9. So we get negative 3y is equal to negative 9. Divide both sides out by negative 3, and we get our answer for y. So negative 3's cancel, and y is equal to negative 9 divided by negative 3 is positive 3. So there's our y. Finally, we can take that y and plug back into either of these two equations that we started with, right? So maybe these two equations we started with here. And I probably would choose the top one. So then this implies I'll plug in 3 here. So I get x plus 3 is equal to 2. Then subtract 3 from both sides. And I get x equal to negative 1. And so my answer, x comma y comma z, if you want to write it like this, you can. Or you could just leave it like this. If you circle your answers, I'm good with that. But, sometimes we just write as an ordered pair. You write negative 1, and then your y, which is 3, and then your z is 4. So that's your answer for x, y, and z. All right. So we've already done 8. So that's all good to go. And so that's the end of our review.